All right, here is your Unit 9 exam review. That's for chapters 27 and 28, where we deal with current for the first time. And what you see here is kind of a breakdown of everything that I think you should know from this unit. I think you should know about the definition of current, that it is the rate at which charge goes by, charge per unit time. And here's another way current is expressed, and we'll go over this equation. This is the charge carrier density times the charge per charge carrier times the drift velocity times the cross-sectional area of your conductor. Then we have Ohm's law. Ohm's law defines resistance for us. The resistance of a conductor is the voltage it takes to get an amp of current to flow through it. And then we'll also talk about it in terms of the resistivity of the material, the length, and the cross-sectional area of the material. Then we'll talk about electrical power and the power equations for that. Then we'll talk about electromotive force, which is a fancy way of just saying a voltage, but it's a voltage provided by a battery, usually. And we'll talk about the internal resistance and load resistance, what's the difference between those two things. And then of course, resistors. We have resistors. We'll talk about resistors in series, how they have the same current, but they split up the voltage. They share the voltage. And that the equivalent resistance of two resistors in series is just the sum of those two resistors, or three or four, however many you've got. If your resistors are in parallel, they will have the same voltage, but they will share a current. They will split up. This is your total current. The currents through each resistor, the sum of those will equal that total current. And the equivalent resistance is equal to this expression here. Then we'll talk about Kirchhoff's rules again. The Junction Rule, which is basically a restatement of conservation of charge. And then the loop rule, which is a kind of a statement of conservation of energy as you move around a circuit. Finally, we'll talk about RC circuits. That is a circuit with a resistor and a capacitor in series with each other. We'll talk about RC circuits that are charging and RC circuits that are discharging, a discharging capacitor with a resistance in series with it. Now, notice what I have here. I've created a little, what I call a quantity chart, and it will just help you keep track of all these variables and units. Here's the quantity that we're using. Here's the variable for that quantity. And then here's how to break down the units. Here are the units, and then some of them, though, like an ohm. Ohms are expressed with this omega, but think of an ohm as the volts you need to get an amp of current to flow through, that sort of thing. So I think this is a very useful thing to study. All right, let's talk about current. And I'm not going to derive everything for this review, but remember what we have in a conducting wire is we've got zillions of atoms. And all atoms are electrically neutral, but the unique thing about metals is that their valence electrons, which I'll only draw the valence electrons, are free to move about the metal, and they just are randomly moving. And this is what gives metal a lot of its properties. It certainly gives it the property of being able to conduct electricity. Because what happens, you flick a switch, and really what's happened is that you've created an electric field in the conductor. And what happens is that these negatively charged valence electrons that are free to move throughout the metal now have a force applied to them, and they start drifting in the opposite direction of the electric field. Because remember, electric fields are defined to be the direction that a positive test charge would be pushed. So we look at a cross-sectional area. Here's the cross-sectional area of that, and let's create two of them here. And so what we have here is a volume, right? And so what we do is we say that that current is equal to the amount of charge that goes by this cross-sectional area per second. It's charge per second, so it's delta Q over delta T, which is coulombs per second. This would give you an average current, but if you want an instantaneous current, you just take the limit and you call it dq dt. Okay. Now, a lot of people think electrons move at the speed of light in a wire, but they don't. They actually move quite slowly. What moves at close to the speed of light is this propagation of this electric field that's in the conductor. But it can be shown, and I'm not going to rederive it here, that the current in the circuit is equal to this thing called N, and I'll go over that in a minute, times the charge on each charge carrier, times the drift velocity, or the average velocity of these moving charges in the conductor, times the cross-sectional area of the conductor. Now, go back, if you want to see this derived, go back and watch that lecture. And there is a problem on the test where you have to solve this problem. One of the things that I'd like to, well, what is N? N is the number of charge carriers per unit volume. So it's a number of things times the volume. And so what units do these have? Well, it's kind of like 1 over meters cubed. Why 1? Well, number of charge carriers, we're just counting the number of charges. Now what is this? This is the charge on each charge carrier. This is the average speed of those charge carriers, and this is the cross-sectional area. Let's look at this equation in terms of units. So we have 1 over meters cubed. We have coulombs. We have meters per second. And we have meters squared per area. And notice what we've got. Meters times meters squared is meters cubed. Cancels the meters cubed. We're left with coulombs per second. That's current. That's current. Now the hardest thing is to figure out what this is. How many charge carriers do you have per unit volume? Well, you have to know two things about the metal. You have to know its density, its mass density, and you have to know its atomic mass, and you have to know Avogadro's number. I always start with the density, like how many grams per cubic centimeter. If they give it to you in grams per cubic centimeters, remember, you have to change that to kilograms per cubic meter. So make sure you make that unit conversion from here to here. And what does that let me do? Well, this is going to allow me oh, and I'm sorry, you don't have to do the kilograms because you'll see them cancel out in a minute. But this will have to be changed to meters cubed. And you just take 100 and you cube it. 100 times 100 times 100, that's 1,000,000. So there are 1,000,000 cubic centimeters in a cubic meter. But anyway, so then you have to know the atomic mass. And you divide by the atomic mass, because what is atomic mass? So this is density times atomic mass. And atomic mass will be X number of grams per mole. Now that cancels out the grams. Well, but I want to know the number of charge carriers. Well, in 1 mole, there'll be 6.02 times 10 to the 23 of those kind of atoms, whatever atoms there are. And then you have to know how many charge carriers or how many valence electrons are available per atom. Usually it's 1 or 2, and that will be given to you. So the number of charge carriers per atom. And so the atoms will cancel, although that's really kind of a counting thing. And now you have the number of charge carriers and the moles cancel per cubic meter. And that's what N is. This is equal to N, a little N thing over there. So it's really not that bad if you use dimensional analysis to figure it out. What is Q? Q is the charge on an electron. It's the electrons that move in a wire. So that charge will be negative 1.6 times 10 to the negative 19 coulombs per electron, right? This is the charge on an electron. All right. And then, of course, cross-sectional area, you can figure that out if I give you a radius or something, pi r squared or something like that, okay? But this is the hard part, figuring out what this N is, so study that, and you'll be in good shape for the test. Okay, now, let's get to Ohm's law. Let's look back at Ohm's law. Okay, this was all about current over here. One ways of expressing Ohm's law is to say the amount of current I get per unit area is directly proportional to the electric field. Directly proportional to the electric field. That is, if I double the field, I will double the number of electrons flowing through that material, through this cross-sectional area per unit time. But how to make it an equality instead of a proportionality, we need to, it's just a function of the material. So we have this thing called conductivity. Quite often the amount of current you get per unit area, that's called current density, which we denote with J. But I'm not going to give you that on the test. That's kind of obscure. But, just to be rigorous, this is a way of expressing Ohm's law right here. But, and if you want to know how we get from there to the Ohm's law that we know and love, which is the voltage drop across a wire is equal to current times resistance, go back and rewatch the lecture for that. I'm not going to cover that for this review. But one thing we have here is this resistance. Resistance, by definition, is the amount of voltage I need to apply to get an amp of current to flow through this wire. Now, if you have a really nice metal like gold or copper, you'll get a lot of current flowing for a given voltage across that wire. But some conductors aren't quite as good, like iron. Iron is really a pretty bad conductor. I mean, it conducts electricity, but it gives off a lot of heat when it does. It has a low conductivity and therefore a high resistivity. And it can be shown, and I'm not going to prove it here, but the longer the wire, that is the length of this wire, the longer that wire, the more resistance you're going to get, the more voltage drop you're going to get, the more electrons lose energy as they bash their way through the conductor. Now, the resistance is inversely proportional to the area. That makes sense. If they're not as crowded, they've got more room to flow. So if you have a big, thick wire, you can get a lot of current to flow through it for very little voltage drop. But if you have a skinny little wire, to get a lot of current to flow through it, you're going to have a lot of resistance. That wire's going to get hot. Okay, so this is Ohm's law that we use the most. And there will be a problem on the test where you'll have to use this equation here. The length of the wire, the cross-sectional area of the wire, and the resistivity of the material that the wire is made of. And this you have to look up on the test. I'll give it to you, okay? But in a homework problem or on the job or something, if you were actually to have to do this calculation, you would have to look up the resistivity for that. Or I suppose you could do an experiment where you measure the resistance and the length and the area, and that's how you calculate the resistivity for a given material. All right, let's move along now to electric power. Okay, so power. Now, if I have a, and this is getting a little ahead of myself, but if I have a battery, a battery's put energy in. Energy goes into the circuit. And here we have a resistor. That's the symbol for a resistor. Here we have energy out. And if you go around in a circle, this puts energy in, this takes the energy out. Yeah, there's a little tiny loss in the wires, isn't there? I mean, that's what this equation is saying here. But let's say that this voltage drop in the wires is negligible. We're going to pretend that these are perfect wires, no resistance for the purposes of this analysis. Anyway, energy out. Well, let's think about this. This has a certain voltage drop, doesn't it? If I put a voltmeter across this thing, I would measure a certain voltage. Now, what does this voltage drop mean? Well, voltage, as we learned in the last chapter, is the amount of energy I've got per coulomb of charge. So for every coulomb of charge that flows through this device, it could be a motor or a heating element or a laptop computer, whatever is using energy for something, that's a resistive element in there. Well, it's got current flowing through it, doesn't it? And when you multiply, well, voltage times current, if I, current, let's just take a look at current. Well, current is how many coulombs go by every second. Well, look what happens when I multiply these two together. If I multiply a joule per coulomb times a coulomb per second, the coulombs will cancel. I get a joule per second. So power is equal to the current flowing through our resistive element times the voltage drop across that. And I'll just call it V, or sometimes it's written as delta V. That's fine. It's just a shortcut. Sometimes we don't always write the delta there. Now, given Ohm's law up here, oh, I went ahead and used delta V up there. Let's just go ahead and put it in there. Delta V. We can solve for delta V. I could put IR here, so I will get I squared R. But what if you want to know how much energy is in? I mean, what do we have here? A voltage increase from here to here, and I've got a current flowing through it. So what I do is I solve I solve for R. There's no resistive element here, especially if we neglect the internal resistance. So we'll solve for R. R is delta V over I. You plug that in here. What am I doing? Oh no, I'm sorry. This is what you use to analyze a battery right here. But if you want, you can substitute in delta V. Solve this for I. Solve this for I and go delta V over R, and you get delta V squared over R. So you can use any of these to calculate the power in a in coming out of going into the circuit from a battery, coming out of the circuit, or just energy flowing in the circuit overall. So there you go. There's power. Now, let's talk about batteries for a little bit. A battery is an electrochemical device where a chemical reaction takes place that drives, that breaks chemicals into ions, and you get a surplus of electrons over here, and you get a lack of electrons over here. That's what we call a positive. Now, if you just have a battery like this and there's no current flowing through it, we call this the EMF of the battery. Electromotive force, which is an unfortunate name, and it's an old-fashioned name, and we're stuck with it. It's a voltage. It's an increase in energy level per unit charge from here to here. Okay. And if you put a voltmeter across a battery, and there's no current flowing through it, you'll get what's called you'll get what's called the EMF of the battery. But if you have a switch here, and you have a resistive element over here, close that switch, now you've got a current flowing in this circuit. Turns out that batteries have their own resistance. I mean, if you get too much current flowing in a battery, that battery can get hot. In fact, that battery can get so hot that it will actually explode. Not in a big, hand grenade kind of explosion, but it certainly wouldn't be pleasant to have it go off in your pocket or in your face or something like that. So don't do this at home. All right. But all batteries give off a little bit of heat, and we call the internal resistance little r. There's the internal resistance. Well, that's the variable we use for the internal resistance. And so now, notice I've got a little voltage drop. I've got a voltage gain due to the EMF of the battery, but if the current is flowing this way, I have a little voltage drop. And the EMF of the battery minus IR, that's the voltage drop due to the internal resistance. Sometimes this is called V sub T, or the terminal voltage of the battery. And this is the voltage that's delivered to your load resistor, R sub L for load. And this is what you're trying to deliver a voltage to make something happen, a motor or whatever. Okay. Now, let's see here, where are we at? And this is kind of going to lead to one of our Kirchhoff's loop rules, right? Voltage gain, voltage loss, voltage loss. So here's the, like if I rearrange this equation, if I put this over here, the EMF of the battery minus the voltage drop across the here, minus the terminal voltage, or the voltage drop across the load, oh, we're back down to zero. We're back to where we started. So that's kind of a loop rule that we learn later on when we study Kirchhoff's rules. Okay, now let's talk about resistors in series and parallel. Let's talk about resistors in series. If things are in series, that means by definition there is one path going through them, and therefore they have the same current. We have charge flowing through this. Now remember, current is defined to be the flow of positive charge. In reality, electrons are flowing this way, but we pretend as if it's positive charge carriers going this way. Sorry, it's just the way it is. So here's I. Here's I'll just call this V, the voltage, terminal voltage delivered, and and so we have a voltage drop here and a voltage drop here. So if this is 0, this might get us up to 20 volts. This might take us down 8, so that means this has to take us down 12, because resistors in series, while they have the same current, the total voltage will be equal to the voltage drop across this guy plus the voltage drop across this guy. Now we know from Ohm's law that V equals IR. So this is I times the total resistance of the circuit. And this is equal to I1 times R1 plus this should be 2, I'm sorry. It's a voltage drop across here, I2, R2. Well, what do we know about the currents? Current's the same everywhere in this loop. Boom, boom, boom. And there is our equation for resistors in series. If you have resistors in parallel, well, you have, they look a little different. Sometimes they'll look like this. resistors, kind of sloppy resistors. So here's my voltage. Now notice that if you go around here, this is, let's say this is 20 volts, for example. If you're 20 volts up here, you're at 0 volts down here. And I can either go this way or I can go this way, but it's the same voltage drop. Any circuit elements in parallel have the same voltage drop. So V1 equals V2. But if this is the total resistance, well, here's I1 and here's I2. Assuming this is R1 and this is R2. Okay, well, the total current is equal to I1 plus I2. Well, what do we know about Ohm's law? V equals IR. So I equals V over R. So this is V over R. And this is V1 over R1. And this is V2 over R2. Voltages are the same. So they cancel out. And you're left with 1 over R equals 1 over R1 plus 1 over R2. And this is the equation you use for resistors in parallel. Now, I'm going to give you circuit things like this. Let me give you something that's kind of fun. All right. R1, R2, R3. Ooh, let's put one right here. R4, R5, R6. This is harder than the one on the test. All right. So, how would you figure out the total resistance of this guy? Well, look for things that are already in series or already in parallel. So this is my total current. R1 has a total current, R2 has a total, R3 has a total current. These guys all have the same current. Therefore, they are in series. So you can say the combination of R1, 2, and 3 is just R1 plus R2 plus R3. So now you can combine these three into one resistor. Look at these guys. They're in series also. So I can say this is R5 and R6. Now what I would do at this point is redraw the circuit if I'm analyzing this thing. Put one resistor here. Oh, this is the R1, 2, 3. And then this is R4. And this is R5 and 6. Back down to 0. Yeah, you can do that. No problem. And now I can combine these by using the resistors in parallel equation. And that will give me R4, 5, 6. And then this will be in series with this. So now you add them together, and now you've got the total resistance of it. And then what if I wanted to know, well, what is the current through this? Well, then you back out. You say, well, let's figure out what this voltage drop is. Then I can figure out what this voltage drop has to be. And then once I know that voltage drop, I know the current through here. Once I know the current through here, I can figure out the current through here. If I know the current through here, I can figure out the voltage drop here and the voltage drop here. So, I mean, you just use Ohm's law and the fact that resistors in series have the same current, but they add, their voltages add, or resistors in parallel have the same voltage, but their currents add, and you just combine it all together to figure out everything you need. And the circuit on the test is really not that complicated, so I don't think you'll have that much trouble with it. Okay, moving on. We have Kirchhoff's laws. I think there's another C in there. I don't know. He's got a lot of consonants in his name that don't make sense. Kirchhoff's laws. Really simple. If you have a junction is a place in a circuit where the current splits up. let's say here's I1, I2, I3. Well, look, you know that the current in has to be equal to the current out. Otherwise, where's the current going? Where's the charge going? You think of water in a hose. If you have 5 gallons per second coming in here and 3 gallons per second coming out, you better have 2 gallons per second coming out there. Sorry, my voice is really leaving me now. Well, what you can do is just say, okay, I1 minus I2 minus I3 equals 0. And this is how you would set up the loop. This is the junction rule equation. Now, if you have a battery, if you're traveling in this direction from A to B, this is a positive change in voltage. Right? If you're going from here to here, if you're walking around the circuit and you go from here to here, that's a voltage gain. But if you're going from B to A, if you're going from here down to here, that's a voltage drop. Pay attention to that. If you have a resistor and the current's going this way, and you're going to go from A to B, if you go from A to B, the energy is being dispersed by this. So if you're going with the current, the flow of charge has less energy here than here. So if you go from here to here, it's a negative, or negative IR. But if you're traveling against the current, you're jumping up in voltage, aren't you? So that's going to be positive IR, a voltage increase if you're going against the current. Now the loop rule says that if I have let's put a resistor here, maybe another battery like this, resistor here, this is R1, this is V1, V2, R2. Let's say this is more powerful than this. So this here you have and you just choose to go in this direction. And you say the current is in this direction. Well, you start here. Voltage gain, voltage loss, voltage loss, voltage loss. So you would go V1 minus I1 or IR1 minus V2 because we're going against it. We're stepping down in voltage, and then we're going with the current and going down this resistor. So minus IR2, and we're back to where we started. So that has to equal 0. What if I decided to go the other way? Let's get crazy and go this way. Well, now we're going against the current, so we're going to jump up in voltage. That's IR2, positive IR2. I'll put a plus there. And then we go plus V2 plus I1 R1. Oh, but look, I get here, I drop down. Look at these. They're the same equations. Just multiply this by -1 on both sides, and you get this, or vice versa. So what you're going to do when you analyze a complicated circuit like this, and I don't have time to work the whole thing. Let's say you had something like this. R1, R2, R3. Let's say 10 volts, 3 volts, something like that. What you do is you pick a junction and you make a guess. Oh, this is more powerful. I bet the current's going to go in like this. I bet this is going to make current go like this, and this is going to make current like this. And then I'm going to say this is I1, this is I2, and this is I3. And then you use the junction rule. I1 minus I2 plus I3. Why plus? Because it's feeding current in. When current goes in, that's plus equals 0. Then you pick a loop. Let's go around the outside. Start here. 10 volts minus I1 R1, because we have a voltage drop here because we're going with the current, minus 3 volts. And then here we're going against the current, so this is going to be plus. Well, maybe I'll combine these into one resistor. Just scribble that on. So what is this? This is going to be plus R3 times I3. And now I'm back where I started, so that all equals 0. So I set up an equation here, and you want to set them up so that you can get 3 equations and 3 unknowns. You need this, you need an outside loop, you can use this loop, you can use this loop, and by the way, it doesn't matter. It doesn't matter which loops you use. It doesn't matter whether you go clockwise or counterclockwise around the circuit. You just have to be careful that you follow these rules for whether it's a voltage gain or a voltage drop. Set it up, and I would use your calculator. Learn how to use your calculator to figure out 3 equations and 3 unknowns. Because really what I want to solve for are these currents. And once I know the currents, I can figure out the voltage drops across each resistor. I can figure out the power out of each resistor and so on. That might be a question as well. Last, finally, remember what a capacitor is. Let's talk about RC circuits. Okay, now let's suppose I have this. I've got an EMF right here. We'll call it an EMF. You can call it a voltage. I don't care. Use the letter V if you like. It doesn't matter. But the book uses this cursive E for EMF for the battery. It's a voltage of the battery. Got a switch. Got a resistor. Got a capacitor. Now, I'm going to graph the charge on the capacitor as a function of time. Well, at time t equals 0, there's no charge on the capacitor. Close this switch. No time has gone by yet, no charge. But as time goes by, current instantly starts flowing at its maximum, but pretty soon we start building up a charge on here. And so when I do, the current has to go down. Why? Because the voltage drop here plus the voltage drop here has to be equal to the voltage gain from my battery. As the capacitor gets full, we get a voltage drop across the capacitor. That means less current can flow through the resistor, which means that as time goes by, as we gain charge, the rate at which I gain charge decreases. And I get a function that looks like this. It's not a square root function. Looks like one, doesn't it? But it's not. It's an exponential function. Now, think about it. What is the maximum? What if the voltage across here was E? Well, capacitance is the charge you get, the maximum charge per divided by E. Coulombs per volt, right? That's a farad. So this right here, it'll approach this, the maximum. Let's call it the maximum Q. And so what you do is you say this is going to be Q over E. This is our maximum charge. I'm sorry. No. The maximum charge is the capacitance times the voltage, right? If I solve for Q, I get CE. It'll approach this. Now just remember, it's always an exponential, so Q is a function of time. And I know it's going to be CE at the maximum. But what I want is when t gets really, really big, I want this to become 1. So 1 minus e to the negative t over RC. If I use this expression, look what happens. T gets really, really big, therefore this whole thing goes to 0. 1 minus 0 is 1. 1 times CE is CE. Now what about the current as a function of time? Current is a function of time. Well, current is dq dt. It's the slope of this. Maximum, and then the slope slowly approaches 0. Maximum slowly approaches 0. Well, you could just take the derivative of this expression. Or you could just say that I is equal, well, what is the maximum current? The maximum current happens the instant you close the switch. There's no voltage drop here, so all the voltage drop is here. So, well, E equals IR in that case, for that instant in time, and I is equal to E over R. This is the maximum current. But this current is slowly going to go to 0. Well, maybe not slowly, but so e to the negative t over RC. Now we derived this, but I'm not going to derive it here. Go back and watch that video on the derivation. But I want you to be able to see how the equation has to match the graph. Okay? Now you should know how to solve for time. If I give you a charging capacitor and I want to know how much time it takes to charge to a certain amount, well, plug in whatever charge it is. Here's your maximum charge. Solve for t. Take the natural log of both sides and do all that. Do the arithmetic to solve for time. I don't have time to do that right now because this is already almost 45 minutes long. All right, now discharging. So this is for charging. You have a discharging capacitor. Well, let's take a look. I'll redraw this. Let's say this is at its Q max. Maybe it depended on this voltage. I don't know. It depends on the problem. Let's say that, though, I have a switch here that's originally open and a switch here that's closed. But then at the same instant in time, I close this switch and open this one. Well, that just, now you might as well ignore this. And what have we got? How is the charge on the capacitor going to change with time? It's easy, you guys. It's easy. Think about this. If you know it's going to be an exponential, and RC circuits are always exponential with time, you're going to say, well, this is time. It's going to start at its maximum, Q max. Now maybe Q max is C times E from a previous problem, or maybe I just give you the maximum. And this is going to decrease very rapidly, but then as it discharges, it has less voltage to push charge through that resistor, and so the current decreases. And it looks like this. And what is this? Q as a function of time is equal to Q max times e to the negative t over RC. And, well, what is current going to be? Current is a function of time. Well, you could take the derivative of this, so if you know how to do that, go ahead. But look, notice that when it discharges, current is leaving the capacitor. When a current leaves something, we call that a negative. See, here the current was positive, right? It's coming in, but when it's leaving the capacitor as it's discharging, that's negative. Now, and look right here. See the slope? The current is the slope of charge. It's a negative slope, isn't it? Maximum negative slope. But then that negative slope becomes less and less and less and less and less. So basically you get this. But then you just have to figure out, well, what is this? Well, the maximum charge, right, the maximum current, well, take the derivative of this. When you do, you get the Q max over RC. And it's negative, right, that negative. Use the chain rule there. It's e to the negative t over RC. Okay. Now what is RC? R times C has units of time. And I don't think I need to explain exactly why right now. That that would be a good exercise for you to study. Why? Ohms times farads equals seconds. It really does. Try it. Do the dimensional analysis. You'll see that it comes out to be seconds. But this tells you how much time it takes to lose, a certain amount. A certain amount. A certain amount. A fraction of each thing that's left. So, and I think we discussed that. This is RC, is called the time constant. We use the letter tau to represent the time constant. For a discharging capacitor, it's when we get to about 37% or roughly of what we started with, the time it takes to lose about 2/3 of your charge. Well, tau up here, right? That's right here. And then tau would be like right here, RC. See, this is the time axis. So this is RC as a time. And it tells you how much. So it's pretty interesting, I think, about how exponential functions work. It's very, very cool stuff. So on the test, you'll have a charging or a discharging capacitor, and you'll have to figure out how much, what the maximum currents are, what the maximum charges are, and how much time it takes to lose a certain fraction of it. Like, let's say, how much time would it take to lose half the charge? How much time would it, well, let's say the time it would take a discharging to you lose half the charge. Well, what does that mean? Well, then that means that if it lost half the charge, Q over Q max, what does that equal? 0.5 equals e to the negative t over RC. See, if you know the fraction of how much charge is left, express it like that. Now you can take the natural log of both sides. Solve for time. Really not that difficult if you know what to do. Okay, well, I think we covered it all, believe it or not. So, isn't that exciting? So good luck on the test, and I'll talk to you later. That is all.